Hi guys, coming in we're going to do a summary of the transformations that you've learned so far through your Desmos activities. We're going to add in the final component to that, which is going to be the phase shift. So when we had done this activity before, in the last set of video, we were looking at f of x equals a sine of bx plus d. And in that video, we talked about what each of the components were working on. Now, in this video, what we're going to do is we're going to add in the one transformation that we haven't really talked too much about, and that's what's called your phase shift or your horizontal shift. Now, typically, when we are looking at this, notice that we are going to use what's called the transformation form of an equation. And the transformation form, really where that's going to come into play is here in the input. So notice that in that transformation form, what we're doing is we're factoring out the b. So just as a quick example of this, if I had a function that was 5 sine 2x minus pi over 2 plus 3, that when we look at that, what's inside of these parentheses right here, this is not in transformation form. To get it in transformation form, you're going to pull out the 2. And because what that will do is that will reveal the horizontal transformation. And when we pull that 2 out, factoring out 2 is the same as taking each of those numbers and dividing by 2 or multiplying by a half is basically what we're doing. When you factor the 2 out, you multiply each by half. So 2x multiplied by half is going to be is 1. And then the minus pi over 2, when I factor out the 2, it's like multiplying by half, and it becomes minus pi over 4. And so what that's going to do for us is that is going to reveal what transformation, what the horizontal shift is going to be. Now, when you look at that, let's kind of relate this back to our transformation anchor point rule that we had done before. What we would have done before is we would have said that x old equals 2x new minus pi over 2. Then we would have taken that and we would have solved for x new, and that would give us our transformation rule. So I would first add the pi over 2 over to the other side, 2x new, and then I'm going to divide by 2, which is the same as multiplying by a half. Now notice that what we're doing when we multiply that by a half is it kind of tells us something about what we have going on here. When I divide by 2 and I go into the transformation rule, we have 1/2 x old and then plus pi over 4 equals x new. Now let's kind of make a connection between what we have here in the transformation rule. So x old, y old would go to 1/2 x old plus pi over 4. And then our 5y old plus 3, which we get from our output transformations over here. Now, look at what happened. We have a horizontal shrink by 1/2, that we multiply each of the old points by a half. Now, that's going to change your period. It's going to change from 2 pi, shrink it by half, it's now going to be pi. Now, remember what we did in the last video with that b value is that b value was actually equal to 2 pi divided by the period would equal 2. So that means that 2 pi equals 2 times the period, or the period equals 2 pi over 2, which is going to equal pi. So notice that both versions kind of gave us the same idea of how we were looking at it. The other way we looked at that too was if b was equal to 2, that meant that there were 2 cycles in 2 pi. And if there are 2 cycles in 2 pi, the original period, that means each cycle is pi. So that gives you, again, the period of pi. But now the other thing that we take a look at in terms of showing this connection is that this shift right here. So notice that this minus pi over 4, and again, it is a minus in the equation. And remember this idea that we always do the opposite of what is inside of the equation because inputs always do opposite. Part of the reason was in the solving process, because it was a minus here, when I solve, it ends up being a plus right here, that to do the opposite, we kind of know that here we went to the right pi over 4. And so notice that in this solving process over here, that I could have done all of this work to figure out that we shifted to the right pi over 4, or I can simply pull out and factor out that 2 over here in the equation. So if I pull that 2 out, notice that what is right there in that position is going to give me that horizontal shift. And when we are doing waves, that horizontal shift has a special name, and it's simply called a phase shift. Because when a wave is shifted over a little bit from where it originally began, that kind of says you're out of phase with each other. And so that's kind of why it's called the phase shift. What this is going to do is it's going to set the beginning of the period where the pattern begins. So basically, taking a look at this, we kind of prefer, and in a lot of cases, our phase shift, we kind of prefer that it is in this kind of transformation form. It's perfectly fine if you guys want to come over here and do the new-old comparison, new-old analysis that we've been doing in Algebra 2 and prior in this year, or a lot of times the shortcut would be simply to factor it out. Now, let's just look at this graphically. So what I'm going to do right now is I'm going to go to Desmos, and we're going to play around with this. So in Desmos, where's my Desmos? Right here. Notice that what I've done here is I have basically taken this and I've put sine of x minus c. So the only transformation we have in there is our horizontal shift. And so I just wanted to show you, right here is the beginning of our period, is this point right here. So if I make c positive, that means that what's inside there is going to be x minus 0.9 or x minus 1. And so you see that it's moving the point that is the beginning of the period right here, shifting it to the right. And if I make c a negative number, which would mean that if I do x minus a negative number, it's actually a plus, notice that the beginning of the period moves over here to the right. Now, from that beginning of a period, your pattern does not change. It's inflection, then max, then inflection, then min, then inflection. And kind of the idea of figuring out where the beginning and end of the period is, it all depends upon what the period is, which in this case is 2 pi, and where you begin. So let's change this. Instead of putting in a number like that, why don't we put in an actual value? So let's do pi divided by 6 as my phase shift. Now I see over here that it begins here at pi over 6, and I'm just going to move over a little bit. And if you look over here at where it ends, now this is going to be kind of given to me in 13 pi over 6. So 13 pi over 6 is where the end is. And if you think about that, that's exactly 2 pi away from the beginning of the period, pi over 6. Notice that we still have these 5 key points in here. It's just each one of them was the quadrantal, and we shifted each one over exactly pi over 6 to come up with those 5 key points. Notice our 5 key points are still equally spaced, where it's kind of like creating your quadrants like we had before, and it's basically just going to shift everything over. Let's look at a different one. If I change this to, let's do negative pi over 3. Right, so if I do negative pi over 3, it now moves the beginning of the graph, the beginning of the period, over here to negative pi over 3. And then my key points, pi over 6, 2 pi over 3, 7 pi over 6, and over here, 5 pi over 3. Now, if you were to take 5 pi over 3 and subtract negative pi over 3 to find the distance between, you would get that same period of 2 pi. So the idea that we really just need to figure out these 5 key points are going to be kind of the important part, so then we can simply add this in. Now let's take a look at what happens if I start adding a scalar multiple in front of this. Now I am going to put extra parentheses around the x minus c so that it's in that transformation form. Now, if you'll remember, if I take this and I would put a 2 here, remember that that shows that there are 2 cycles every pi. Now I'm going to just kind of take this back and let's make c 0 for a moment. So you'll notice here that it starts at the beginning here, which I've kept highlighted with the 0, 0. It ends now over here at pi, and then a second period over here at 2 pi. So you see how we have 2 cycles every 2 pi. Now if I were to change this to 3, then you'll see that I move over 2 pi over 3, the next cycle ends at 4 pi over 3, and the next cycle ends at 2 pi over 3. But now the period of the graph is 2 pi divided by 3. There are 3 cycles every 2 pi. And so it kind of start to see the repeating pattern that we have. Now, the question then becomes, what if c is not 0? So let's take a look at my graph. And what I want to do is I want to move this beginning back here to negative pi over 3. So do you see where that is right there at negative pi over 3? So if I add c in, and we're going to put that in as negative pi divided by 3, now I see that we have shifted over. We are still going to have, as we take a look at this, here's the beginning of the period, here's the end of the first. Notice that that is exactly 2 pi divided by 3 long because there are 3 cycles every 2 pi. So period is 2 pi over 3. And then here's the third, and then here out to there. So from here, negative pi over 3, all the way over to here, 5 pi over 3, that's a distance of 2 pi, and you'll see that we have 3 cycles in that graph. But notice that the beginning of the period moved over here to the left, negative pi over 3. Up here in the equation, what we actually would have had, and I'll just type it down here again just to kind of emphasize that to you, that we would have had sine of 3 parentheses x plus pi divided by 3. There. So this is what it would look like with c equal to negative pi over 3. And you can see it's overlaid right on that. I can turn that off. We can see the original, and you see that it's overlaid on that. Now notice that different forms, and this is kind of that whole transformation form of what happens when we multiply it out. So if I have another one, I'm going to call it h of x just to give it a different name, even though it's going to be the same one. Sine of 3x plus and pi. And notice that what I've done there, and again, that lies right on top of the ones that we have. If I turn that off, you can see it's in the original. See how these are algebraically equivalent to each other. So the phase shift, you know, you would be tempted if you saw h of x down here that you would say the phase shift is left pi. But whenever you have this 3 in front, where you have a horizontal scale and an addition here, you have to factor that out or do the new old analysis to figure out what transformations have happened. All right, so we're going to take a pause on that. We're going to come back in here and we're going to do some practice problems in the next video where I kind of show you the different types of problems that you might see and that you're going to be required to work with. But again, this is kind of the main idea of the phase shift that we're looking at.